Hello everybody, I'm very glad to announce that today we begin with new series of webinars for midas and FX, which is called In Practice. So during upcoming sessions we will present more practical content in regard to functionality and practical usage of midas and FX. So topic for today is geometry simplification. So today I prepared four major topics. During introduction part, we will go through some basics, starting from question why do we need simplification. Then I will back for the moment to some basics and we will define geometry, we will look what topology means, I will show you some short information about 3D modelers and how they are reading geometry to create some solid background for today's webinar. Next, content will be focused on the feature-based modeling and simplification process. I will introduce geometry simplification tools with related examples. Simplification process, as you know, can arise some challenges and issues, especially in regard to topological changes. So a few comments about them will be given to you as well, and I will talk about obstacles and the ways how to overcome them. So why to simplify? So there are many reasons, but the most important fact to know is the decision which feature should be removed or suppressed depends on us only, on our engineering decision, experience, and of course up to context and application of our simulation model. So usually holes, fillets don't affect solution accuracy so much. However, presence of small geometrical details influence numerical size of the model, and in this case solution time can be also longer. The other reason is meshing and related issues, because due to topological issues meshing process cannot be accomplished, as well as due to presence of wrong topology. This issue can lead to creation of highly distorted elements, which again affects solution stability and accuracy. So geometry or topology. So as engineer, and I hope you are engineers as well, we think, and I assume basically that you have heard about those terms before. So you've heard this word topology before, but can you really point the difference between geometry? Do you feel what is this exactly? So if not, or if you are still confused, please take a look on short explanation. Let's take a look on the presented picture. Basically, let's compare two shapes that I'm pointing now. So two objects can have the same geometry, but different topologies can be present in the same time. So what is the difference? Just according to the definition above, geometry is called metric information, and it explains, or it gives information about actual dimensions that define entities of the object. So in our case, the entities are edges and points which are not shown at this moment. So if we compare length of each entity, like length of each edge, and if we compare values for radius, we can see all of them are the same, which means geometry is the same. But the topology, which means the method how those edges are connected, differs, because in that case circle is placed inside rectangular shape, in that case is placed outside, and vice versa, which means if we take a look at the same picture at the down, we can see that we have the same topology, but geometry is obviously different, especially if we compare the length of L2 on the left side with the right side. So now it's easy to figure out that some part of simplification process is actually integration with topological changes. So the next case, the next thing is to realize and understand how geometry is being represented by your modeler. Being represented means how it is created and what features are implemented there, how it is displayed. So, as you already know, geometric modeling is the core activity of CAD system, and it contains all geometric and topological information describing 3D objects. So generally speaking, there are many digital representations of 3D components which falling into the category of solids, but for today's webinar I would like to focus on two of them. So the first one is called constructive solid geometry, and using this method, your modeler will give you tools to model geometry using Boolean operations only, and this modeler will store primitives like cylinders, cubes inside the file. But to create all of them, you will use operations like union, intersection, simply, as I said, Boolean operations. But in case of boundary representation, the CAD engine will process the skin of the object only, and basically model which is created by this way of creation contains the result of the operations, which means it's much more flexible for more advanced operations. Like, for example, it can work with NURBS curves or NURBS surfaces. So at this moment, I will not talk about advantages and disadvantages of both ways too much. Basically, what I would like to say that most of the modern CAD systems uses both approaches. That's the information that you should keep in mind. So two categories of information are stored in BREP model, so geometrical and topological information. So since topological information is stored inside BREP model, all you have to know now, from my point of view, is the orientation of sub-shapes. This is quite easy to understand, but from my experience, our users and generally FEA users have problem with understanding of orientation, since this is strongly related to meshing process. So, for example, if we explode our model into sub-shapes, you can figure out that this edge has some kind of direction. So when you start to use more advanced features like mesh seed, then you can see how nodes will be distributed because of the direction of the edge. For 2D case, when you start to mesh model with 2D elements like plates, the result can be presented similar to the picture I'm showing on the slide, which means some part of the faces can have opposite direction, which means if we start, for example, to review output like bending moments, the result can be mismatched, can be inconsistent. So that's one of the reasons. So please keep in mind and check the orientation as well. We have tools inside NFX, but I will talk about this during next sessions. Okay, so next part presents topology of geometric entities you can find inside midas NFX. If you want to create solid, you can start even from the point and follow up some of the path. But it would be nice also to know how exact topological entity is stored inside your modeler, in our case in NFX. So for example, for the box which I'm showing now, this box cannot be simplified since this is not solid. This is a topological combination of individual faces, and this feature don't have volume, for example. So you have to know and understand how to use it. So both solid box and shell box look the same, but checking property is recommended. So again, the most interesting thing is to know how the lower level topological information is stored according in compared to the higher level entity. So if you look on the midas NFX tree, you will see that the geometry created is stored independently. This information, you can find information about history of your modeling, but in this case, this is not parametric history modeling. So each lower level shape can be stored at the way how you started to create your shape. Similar situation is coming with import of the geometry, so there is no history, but you can import a shape which has some topological information. So this is what I was trying to explain before. We don't have history, but we still have some topological information hidden inside the model. Just to give you some additional information, if there is a need to use this tool, which is called explode, if there is a need to go back or extract lower topological shapes, you can use this tool and simply explode the geometry to edges or faces for your editing or simplification as well. Feature-based modeling. So having background presented before, we can start to talk about modeling and go slowly to simplification process. Feature-based modeling is a very known concept, approach, and it's still widely used among many engineers. So I think there is no special need to talk about this concept. However, I would like to emphasize two modeling approaches using this technique or based on this technique. So first way I'm calling addition, and second one is subtraction. So let's see video first, just to compare both results. This is very short video and I will make pause soon. So let's start from the first step. As you can see, we are starting from the primitives and they differ a little bit. Okay, the next step is creation of the additional solid, and as you can figure out, the next step will be Boolean operation, which is add, and in opposite case I'm subtracting volume and I'm creating my bracket in a little bit different way. So the rest of the steps are pretty much similar because feature-based modeling is simply a philosophy from create something from a simple shape to complex one. So that's the basic law, we can say. So now finally we're touching simplification process of cut solids. So before meshing step, simplification is a way to enable a robust mesh generation and to obtain directly the shape required for FEA without some local adjustments for a finite element mesh. So simply saying, we have initial model and based on our judgment, we are removing unnecessary features or even changing model dimensions. So simplification is not only feature removal, which I will talk about right now. Simplification of 3D solids can be done using two approaches inside NFX. The first one is called defeaturing or feature removal, and the second one is topology adaptation. So now, as you already know, by topological change, we are changing associativity of subshapes, like for example, for that case where I'm removing this face and as the result, instead of two edges close to this corner, I have one edge and at different position. So I'm changing the way how those faces are connected. And the second, very easy to understand approach, which is called feature removal, and everybody knows more or less how it works. So let's look on the meshing result. As the result of topological adaptation, we can see that element distribution close to the corner and close to the top of the bracket has been drastically improved. So let's take a look on our result. So element concentration has been eliminated, and this can be potentially source of extended calculation time or source of some inaccuracies. So in my model, element concentration has been created due to presence of the small edge, but at this moment we don't know exactly how to find small-sized entities. And during the webinar, I will show you some tools inside NFX how to do that. So before we say anything about tools which can be used for simplification, let's ask ourselves if simplification process can be fully reversed. This is a very trivial question, and I think, but anyway, we have to spend some time to think about this. So I refer to the slide with the animation, a few slides ago. I was showing to you a few slides ago about two modeling ways, addition and subtraction. So as you can see, the featuring process will lead always, at least theoretically, to obtain a primitive shape, and it can be recognized as opposite to this subtracting approach of modeling. So we are going at this way. This means it's not possible to get two independent blocks by direct defeaturing, since the base feature was initially created by Boolean operation. This is very important comment because thanks to this you can make a good strategy for your simplification process. The most challenging part of it is to imagine sequence of the features which has been used initially to create complex shape, and then we have to make some strategy to reverse the process. So how to find small features, which tool should we use inside NFX? So basically, if you go to the tools and if you click simplify, you will get access to this window. So finding some details is very easy using NFX. We can click on use automatic search, or we can go to manual options and remove some features manually. Description of search condition has been given to the right. So on the next slide, I will back to the example, and we will follow up some cases. Just let's take a look briefly on the description. So holes will be found globally just right after import of the geometry, but if you want to change limit value, just simply please provide value that you are looking for. So basically we can do that by initial guess, or we can investigate our edges sizes in our model. Defining fillet is very easy. We can also provide fillet value. Small edge, we are inserting value of the edge in regard to any edge on our model. Small face will be found according to the longest edge of the face. So if we have some small face, we are looking for the longest edge of this small face. Sliver face defines the width of the strip. So this kind of small detail is actually defined by the ratio between the edge and the area. But for easiness of usage, we are looking for the width of the simple strip. Spike will be explained on the next slide. And as you can see, results or all entities which can meet criteria will be listed, and we can follow up the values. Okay, let's take a look how automatic detection works. So right now I will show you how to find some details. So I prepared this geometry by myself, so I exactly know which value should be inserted, but those numbers like 8.53 has been estimated by the software automatically. So let's take a look about search. So now I'm looking for the hole. So if I type value more than 40, I will get that result. The fillet has value of 50, so exactly the same situation. I can get information under results. If I type more than 50, always it also will give this value. So small edge is the next feature. So 0.1 millimeter. So according to this condition, I'm presenting how to find small edges. So this edge has a length 0.05 millimeter and it's placed there. If you click if you provide double click, the model will be magnified and you will see your detail more close, from close perspective. Small face. One more time, small face is the length for the longest edge of the face. So we have small face there, but let's say according to my criterion, the thickness of the solid is 30 millimeters. This is why I'm capable to see it. Okay. And the second is free. This value represents area. Okay, so basically what we can say, this one has 30 millimeters and this width is 2 millimeters. This is why we have 60. Sliver face is the input of the width of the strip. In my case, I will use 0.11. So I found some sliver face. Again, the result is pretty much similar. And finally, I will look for the spike. And I will show you on the next slide how to find the spike. So what I did at this moment, I specified value of 1 millimeter and spike has been recognized. Actually, two values are related with the spike. Okay. So what is the spike? Spike is simply geometry which has kind of edge disturbance, which looks more or less like a triangle, and this number stands for the spike width. So basically, we are looking for this distance. So next video that I want to show you shows the featuring. So let's take a look how to use automatic function to remove all of the features. So in the same way, I'm removing fillet. So this is very easy feature. Some edges are still present. I'm looking for small edges. Again, I remove the small edge. And I think now I will start to think how to remove the small face that I was showing before. So basically now I'm looking for small faces. And the result right now is 0 because small faces has been removed automatically according to the fillet option. And sliver face. Sliver face, there is no result according to this criterion, but width of my spike is 1 millimeter. This is why when I type 1.1, I will see several edges. So there are many ways to remove this spike, but I would like to point to you some feature of this spike. So if we remove all of them automatically, we can still meet some issues. For example, like now, using small face, I would like to remove this spike, but the problem is this is not spike anymore according to the tool that we have. So we have to figure out or find the way how to use it manually, using manual options. I will show this later, or using those options what we have in auto search. So for the moment I used auto search, and as you can see, Topology has been changed and there is some edge still there, so I can fight, let's say, with this issue, but I will simply make undo and I will fix this problem by removal of the small edges. So step by step I will delete all of them. And now it's very difficult to see if there is something still present in my model. So I'm still using search condition to figure out small edges, small faces. And that's my final search. I will use sliver face. So that's the value of area. And I will click remove. So now the model will be simplified. Okay. So let's move with manual selection and removal. So this is the option that you can click just next to auto option. So I'm starting from the option which is called show hide verticals. Basically, we are using this option to see if some edges are broken. And just using remove point, I will merge two edges. So as you see, points disappeared now, and the geometry looks better. Small entity search. This tool works similar to search condition from the previous tool, but as the result, we don't have legend, but instead of that we have indicators. So if we type our search condition, some areas will be highlighted on the presented way. So I will skip this video a little bit. I will go to remove face option, and now you can see that using this option we can very quickly delete the face. Okay, so there is no change in topology. Now I'm using remove face again just to remove the fillet, and I'm merging faces. And this is how we made simplification using manual tools. Just to back for the moment, if we want to see, it was everything. Okay. So manual selection and removal tools works in following way. So this remove point works like this. If we select this point will be removed, but all of the topological information will move in the closest direction to the previous definition. So this is why those edges will move to this way. Remove face is very simple to understand. It's very simple to remove this packet by the selection of the faces. So you have seen this. Merging face is simply a removal of the imprinted curves from your faces. So this is exactly how it works. So the next video I would like to show you is topology adaptation. At the beginning of the presentation, I told you, like on the bracket, I will present to you how to deal with this type of work. Of course, model is very simple, but it will give you some idea. So now I'm looking on some option which I will explain a little bit later. So the value was 180 degrees. So let me start to do the model. Right now I'm going to import. I import the geometry, so what we can see is the same geometry as we've seen previously inside PPT. And let's try to simplify this geometry that I'm showing now. This time I will not use simplify tool to look for small entities. Instead I will use check geometry option, and I will use small edge. So if you check this, all of potentially small edges will be highlighted. As I told you, at the first stage it's very difficult to figure out which value we should use as the limit value for simplification tool. So now we know the place, and we can simply measure this feature. So now I have got first value, and I'm going to check other place. So I will speed up a little bit this video. So now I'm using manual options, and I'm going to remove this detail by remove point. The problem is actually the attribute of this option is we cannot select few points in the same time. We can only select one point, and using remove immediately option we can delete one by one points, and as you see, edge moved directly to the corner. So we are doing the same with the opposite side. One point and second point. And now let's try to delete long edges. Let's see if it will be possible. Okay. So first one is okay, but I think there is some big topological change to the face of the bracket. So the second edge cannot be removed. So I think there is a huge change inside this part of your model. In this case we can remove something, but now it's not possible to do anything except of the top face. So for example, this side cannot be simplified because of the topological issue. Okay, so how to overcome this issue and how to change the topology of this model? Solution is very simple. I will display second model, that's the copy of the previous one. And let's make projection of the curve onto such face. So this is the hint. Okay, I have edge. What I'm doing now is selection of the top face, face number 1, face number 2, and third face. Now I'm setting up direction for the projection. Checking, so the result is exactly as I'm expecting. And let's click on OK to see the result. So now if we proceed with Simplify tool, we will see the difference. Let's go to Manual tab and let's use Merge Face tool. Remove immediately edge number 1, edge number 2. This is why it's important to understand your modeler. This is what I was saying at the beginning. So now, as you see, it's possible to do such topological change. So if we go to mesh, before mesh, I will delete fillets. So if we go to the mesh, there is no issue, and there is no concentration at the corner, and mesh looks pretty much okay. Okay, at the beginning of previous video, I was checking option which is called Split Revolved Faces, and this option automatically divides faces with curvatures of cones, fillets, holes, according to specified angle value. So this is really important for us since topology of imported geometry will differ depending on this setting. So default value is 90 degrees, but for some cases, especially for simplification is one of them, this value can be changed, as I did for my example where I specified 180 degrees. I made this to allow me to delete edges. As you have seen, it's recommended to check geometry by doing simple meshing before you proceed with advanced simplification, because one of the issues can be actually information lost about circular faces. So please use this feature carefully. So this will determine the rest of our job. So this is pretty much important option. Actually, is hidden inside options. Final example is the example with more complex detail, and this example I made kind of 2 years ago. So I was not well user of simplification tool. This is why it took a little bit more time, and I was recording every my step. But I would like to present to you some guide which can be helpful for other complex models. So basically, I'm using the same philosophy. What I'm looking on my part and I'm seeing is kind of symmetrical. My geometry has a plane of symmetries. This is why I'm dividing my part just to save some time during the simplification process. Now I'm hiding the part. So that's the first step. The rest of my job is simply looking and investigating the shapes. I'm trying to imagine what will be the order of feature removal. So I'm trying many things. For example, I will divide solid at this place, and I will hide this part, and I will focus on this part of my solid. I think that's the good approach, since you can save a lot of time. Okay, so let's move a little bit with this example. So I'm going to time at 6 seconds. So I'm dealing with the fillets. If we go a little bit more, you can see how geometry is being simplified. So 2 big fillets left. I'm clicking remove. So one of them has been deleted, and by using manual tools, I have to merge some of the faces for this top fillet, I think. Yes, there is some issue, so I have to go repair shape. I didn't say anything about this shape, about this command, which is called check shape and repair shape. This works. These are giving us some default settings which are implemented inside the midas NFX algorithm, but I think I will talk about this a little bit more during the next session. I didn't prepare anything. I'm sorry for that. But topology optimize algorithm is actually widely used, since it repairs consistency of your edges, faces, points. So this is why I'm clicking right now on this. I'm simply afraid if this information has been lost, or there is some internal error. This is why I'm using this. Simplify, it works similar to simplification of the fillets, but there is additional criterion. I don't have examples, so this is very difficult to explain. Okay, so if we go to the next part of this video, you can see that there is a huge progress in terms of my model. So everything looks really nice, but the problem is, like, I met some problem with meshing. So if we go to the mesh, and if we rotate this object, you can see that some element is outside the geometry. So this means something is wrong with my geometry. I will back a little bit, and I will make pause again. Oh, I'm talking about this place, which means I still have to find solution to fix this geometry. So meanwhile, I'm doing a lot of operations. I'm merging faces. I'm cutting my model. And finally, I made model without any issue. So that's another obstacle you can meet during your work. And finally, after some work, we can compare both geometries. So everything works fine, as you can see. So now let's see a simplified model and original model. So I think this is really nice toolbox for fixing the geometry which you can use inside Midas and FX. So just to summarize today's webinar, you have to plan your simplification strategy. Basically, you have to start from investigation if your model is symmetrical. Subdividing on the small parts is also recommended. This will give you additional flexibility in terms of removal of some features. It always requires a little bit experience, because even if we think that something is easy to remove, for example, if I want to remove this edge, usually I can get this result, but order of selection is also important. So if I click this one, I will get a proper result. So always verify your meshing result after simplification, because you can waste a lot of time when you don't do that. Okay, thank you so much for today's session. If you have more questions, please let me know on the mail. I hope you enjoyed, and thank you very much, and see you soon.